Hello, welcome to numerical ship and offshore hydrodynamics. Today is the lecture 46. So, today we are going to continue the discussion about the time domain panel method. In previous class we have discussed about the static, how we compute the static hydrostatic components and other things. Today we are going to discuss how we can compute the hydrodynamic components. Okay. And these are the keywords that you have to use to get this lecture. Okay. So, let us start. Now, you know that this formulation is based on the earth fixed system, and when we start applying this equation, before that we have transferred the body coordinate system into the earth fixed system. If you remember that we said that when you compute the phi, when you compute the phi t, we are actually finding out the phi with respect to the body coordinate system. Now, then actually we have to find out this del phi del t in the earth fixed system. So, you can call it the E is equal to del phi del t into the body fixed system minus u into del phi del x. Now, this is actually in case of a 0 speed, when you do not have this the forward speed part, it is going to 0 because equal to 0, but when if you want to do it in case of a forward speed. So, along with this we have to add this u into del phi del x term. Okay. So, so this is how I can get the pressure term. So, it is simply you are using the forward difference scheme. Now, once we get this del phi del t term, then we have to integrate over the body to get the forces. So, we are integrating, it is rho del phi del t and multiply by the n. So, then we are getting the force, and also you can take the moment, this also if you take this normal you can get the moment. We have we discussed about all this normals n and what is x cross n. So, today we really do not take much time or any time to define, I mean to tell you what is the x dash cross n dash or what is the n. It is very well. Now, this actually is a forward marching scheme. Thing is that we are getting all the force and momentum about the time step t. So, our idea of any time domain code idea is I am getting it at time step t, and then we are using some kind of numerical technique to get the velocity in the next time step, which is v plus delta t, and also we can get the displacement also in the next time step t plus delta t. Now, I did not mention, I do not mention here any particularly what kind of scheme you have to use in this particular case, because there are many, right. So, you can use here, I mean if you ask me what to use, I will prefer to make delta t small, I prefer to make delta t small, and I can use the Euler scheme that actually what we used in when you use the impulse response function code, when you wrote that also use the Euler scheme. So, it is pretty robust if you make delta t little bit smaller. However, there is a Adam-Moulton predictor character scheme is available, or maybe that Runge-Kutta that is also available, right. So, you can use any kind of such scheme to find out the velocity and the displacement in the next time step, right. And now, at this point, after having lot of, I mean almost the 45 class, we should know, I mean we should not ask the question about what actually I wrote here. Now, this is nothing but I am solving this m into v dot, which is m x double dot equal to f, and from there I just try to figure out my v plus v into t plus delta t is nothing but it is f by m into delta t. Now, if you are using a Euler scheme, you really only need the two component, right. If you use the Euler scheme, you only need about here that f t plus delta t or maybe that v t plus delta t and delta t t plus delta t, and here you need that v t and then delta t, and then actually you can use any linear scheme, right. So, this is how we can do that. However, if you want to use some higher order scheme, so then you need this f t minus delta t and f t minus n delta, depending on that what scheme we are going to use, right. So, everybody aware of all this, how to solve the ordinary differential equation and get the velocity and the displacement in the next time step. So, this is the scheme that people are going to use to get the velocity and the displacement in the next time step, right. Here I really do not mention about the schemes, right. This is the many schemes available. You can take any one. If you ask me, I would take Euler scheme, which is most easy. It only have the linear approximation, or you can take the higher order approximation using the higher order method. You can take predictor corrector scheme. Now, here actually we are using the predictor corrector scheme. Why? Because if you look at this, so first let me rub everything. Now, if you look at here, when you get the velocity, we are taking the force at the time t, right. Because if you remember, I just write the Euler scheme, it is nothing but some value y t plus delta t, it is nothing but y t plus dy dt into delta t. So, this is the Euler scheme. Now, dy dt you can take at, now if it is t and if it is t plus delta t. So, this slope you can take either this point or that point based on your going to use the implicit scheme or explicit scheme. Now, here the same thing here, unless you have single, you can approximate this solution maybe in a curvilinear fashion. So, in that case you need more points. So, therefore, you can take many parameters f t minus delta t, f t minus 2 delta t, so many parameters to fit a higher order curve, right. However, the point is that I am actually using the, when you try to figure out the velocity, I am using the force at time t, right. But however, when you calculate the displacement, I am using this updated velocity, right. So, this is what you can say, it is a predictor corrector scheme. Okay. So, and now it is your choice, you can take anything. In fact, you can use Euler scheme and you can use the same thing, right. In fact, that is what we did in our code when you develop the impulse response function, right. Anyway, so now second part is how we are going to evaluate the Green's function. Now, here you have two parts, one is the G0 and another is the GF, right, and this is the expression for R, it is the R dash and it is the R, and J0 is nothing but the Bessel function. Now, what is this R dash and R? Let me see in the graphical manner, I mean it is better to see this graphical manner. Now, suppose this is a point, a source point P, and let us take this is another point, the field point, it is let us say q dot or anything, and here it is called the field point. And then if you take the image about the horizontal plane, so that means if I draw a horizontal plane, and now if I have in the below, I have the source point and maybe I have some field point here. So, if I take the image about this horizontal plane on the top, so that is nothing but your the image point, or you can call the mirror about the mirror point about the xy plane, horizontal plane. Now, here if I add this point P to Q, So, source point to the field point, that we defined as r. So, this is nothing but the difference between source point to the q. And then you have another point which is r dash. Now, r dash is nothing but the distance between the source point to the image point. So, r dash is nothing but p minus q dash, or q dash is the image point. So, this is the definition for r and r dash. Now, what is capital R is nothing but the projection, right. So, that is why we write this capital R is nothing but capital R square, it is x minus y square plus y minus eta square. So, this is the distance, or you can call it projection. So, this is the definition of r dash and the capital R. Okay. And these all things are used here. So, here you can see the r, you can see the image point, it is z plus y, right. Now, how we compute this? Actually, we do a transformation. So, what the transformation we are doing here? We are using a 2 by 2 cos quadrature rule to do that. Now, here we do not have the sufficient time to tell you about this numerical scheme of this how I do this beta and mu. I mean of course, I am going to tell you that what is the numerical scheme, but in detail in coding we do not get the time to do the coding, but here I can promise you one thing, like at the end I can provide you at least the MATLAB code of this the evaluation of the free surface Green's function. Okay. Of course, at the end of this course. Okay. Now, here we can non-dimensionalize, actually what I am doing is that we are non-dimensionalize the Green's function. Now, remember this Green's function actually have 4 component. One is p is nothing but the source point, and t is nothing but the present time. Now, it is actually called the impulsive Green's function, or you can call the memory function. It involves a memory function. What is that? Like suppose at present time I try to compute that contribution of the source potential, but it is not sufficient to only consider the impulse that is I am providing right now at let us say some t equal to let us say 10 second. I am giving an impulse and I am trying to figure out that what is happening because I am putting this disturbance in the wave field. Now, it is not sufficient, right. Already we have shown a picture, like in a glass I put a ice, I can see there is a memory effect. So, it is not enough only to consider the existing the impulse. Also, we need to consider some impulse that I am giving the impulse starting from the 0th second. So, at the 0th second, the first time I put impulse, and again in the first second also I put another one. So, in each second actually I am going to give one impulse. Now, at 10th second it is not sufficient only consider the impulse, I mean the effect because of the 10th second impulse. We need to consider the 9th second, 8th second, 7th second, 6th second, all this combined effect also we need to consider. So, that is what I say here that p is only the function of t, that means that my source point the field point actually it is there at the present time step. However, my source point it is actually function of the tau actually runs from the tau is actually runs from 0 to t. It is strictly less than t, of course, it does not take the present time step, but actually it should be 0 to less than equal to t minus delta t till that point. So, this is the limit for tau. So, in that way I am considering the effect from the 0 till the t minus delta t second. Okay. So, now, so this is how actually I that is why we see that Green's function taken care of all aspect is taken care p at time t and q at time tau. So, now we need to non-dimensionalize the whole thing. So, this is how we non-dimensional t in this form, and also we non-dimensionalize the p and q in this form. Okay. Now, let us see in the picture what actually it is. So, eventually this b p t q tau turns into this g by r dash g into mu beta. So, I am shifting the coordinate. Now here actually I have to deal with the 4 parameters, right, and this is actually very difficult. How can I can I handle this p and then q, then t is at 4 dimensional variable. So, then I use this transformation law to make this 4 dimension into the 2 dimension variable. Now, we are comfortable of dealing with the Green's function in the domain of mu beta, and of course, once we get the value of mu beta, I mean g in mu beta, definitely we need to go back to the original p t q tau in this domain, right. Definitely we are going to do that. Now, if again this is actually the integration scheme in the mu beta coordinate system, right, and before that also I would like to see here that about this transformation, that is mu equal to z p t plus z q tau by r dash. Now, what is the meaning of this? Now, you see here from this picture I can draw a nice thing. So, if this is the time scale, so I am here, I have this p t. So, then I have this image point over here, sorry, source point over here, and at some previous time step tau, right, and then I have image over here, and then actually this is my r dash, and then this is somehow it is my the image point. So, this is my and now if I do this, then you can see here that my transformation is nothing but z it is z coordinate of the present time step plus it is the z coordinate of the previous time step, right. So, and divided by r dash. So, now how I can idealize this? So, it is very important to see this idealization. So, if this is the r dash, so somehow we can think this this is the z. Now, if I project here, so it may be this is the thing, and then this r dash or you can image, you can take this r dash. So, ideally we can think this is something a coordinate system. Now, if you make a theta, so basically mu I can think of in terms of some sine of theta, because this is the hypotenuse and this is the height. So, this is it is not actually like this, but somehow actually we can idealize the this mu as it is behave like a kind of sine theta. Okay. Similarly, this beta you can it is the beta, if you look at this, idealize the beta, it is the time scale. So, this is your nothing but t minus tau, this is the length and this is the hypotenuse. So, then beta I can idealize the beta as cos theta. It is really we cannot say sin theta cos theta, but you can thought of that this mu and beta actually it playing this role by sin theta cos theta, because in that way you can at least try to see the thing. Okay. Now, once we do that in mu beta system, then actually I divide the whole thing in some domain, right. In the mu beta, if you look at it, that only it should be lie between 0 to 1, right, because if you look at this idealization this by r dash. So, it is the maximum value it could take as actually 1, and when you get this value 1, can you think of Yeah, let me just rub the whole thing. I will show you that when this it could get the value 1, like in this domain. Now, if I take a point here, now this is my z t, and if this is my z tau. So, if the both point lie in the same horizontal line, at that time actually your r dash and this difference become the same. So, at that point this is I mean the only when it could be a 1, otherwise in any other situation this is your r dash, and actually this is the difference, right. Z t plus z tau. So, this is you can think of this is the difference, these are z values. So, this cannot be more than 1, I mean more than r dash, right, okay, because this defines the hypotenuse and this is just a one length or height. So, we understand that value of mu it should be lie between 0 to 1, but the t minus tau can go to infinity, right. So, in the horizontal axis, the beta axis it run from 0 to infinity, then the vertical axis mu should 0 to 1. Now, here this scheme is very popular scheme and it is given in many books. You can see the Newman's book or some very thesis early not early, that like late 80s thesis, all the theses have this scheme. Okay. Nowadays, again I am telling you that solution of the Green's function is not unique also. This is how we solved it, and in fact, in late 80s or early 90s people use this, but however, later stage this can be, I mean people actually transfer this into a ordinary differential equation and can get, and they are getting some analytical solution also, but all discussions is a very long discussion. So, let us stick with one which is nowadays if you are doing a MATLAB code, these things are very easy, because in MATLAB they have inbuilt Bessel function, then Phelan integration, series expansion, asymptotic expansion, everything, all this component you can get into the MATLAB. So, writing this code in MATLAB is nowadays is not that difficult. Okay. So, anyways, the only thing you need to do is you need to figure out that when you do the integration. Now, suppose I am doing a Gauss quadrature rule to figure out the integration. Okay. Now, maybe not today, but definitely in one class I am going to show you that how we are doing the integrations thing. So, that time again we can come back to this, and we are just showing you that how to use this chart. Okay. How to use this chart, that time we are going to show you. Today we are just telling you one thing, that when you do this integration of the, so now when you do the integration of Green's function, there is a two component, one is runs with the G0, another is running with the free surface Green's function GF. Now, when you do this integration numerically, what you are going to do is, from here you are transferring this into that G P T Q tau, all four values, is it not? Suppose you are running it let us say at 10 seconds. So, now let me here only I just draw this picture, okay, it is easy. So, now this is your panel, this is your panel at times tau, and now let us take your move the ship at some point. Now, here this is your the updated position of the ship, and you are taking some value over here p, and this p is at the time t. So, what we are going to do is, suppose now with respect to this t, you are figure out this is your source point q. Now, right, that how I do this panel in that panel method, how it works. We have to have a p and then we have to have a point q, right. So, now this q, it is at the time tau. Now, when you are doing the integration, the information about the p, you know the information about the t, you know the information about the q, you know the information about the tau. So, definitely if you apply that this previous thing, that if you apply this these two equation, then easily you can transfer this p, t, q, tau into the mu beta system, and then you know the corresponding value of mu and beta also. Now, you are going to check that in which range you are going to get the value. It is fall into this Bessel function region or Fuller integration or series or asymptotic, anything, and then you apply those formulation and you get the value for g. Now, once you get the value for g also, you can again very easily you can get the value for del g del mu and also del g del beta, that also very easy you can get. Now, using this technique actually you can get all the component, you can now g already you can get, then del g del x also you can get, del g del y, del g del z, del g del t, everything you can get from this expression once you know the value of g and then del g del mu and del g del beta. Once you have this value, you can get all this value over here. Okay. We are going to discuss about the numerical instability. Very quickly I will tell you this. Here we can see there is a graph. So, now the tau is nothing but your the beta. Okay. So, do not confuse the tau, it is tau, sometimes we can use tau also, it is a mu beta, let us say. Now, you have this axis mu, you have this axis beta. So, I can see that when this mu is 0, the Green's function is become very oscillatory in nature. So, that means when mu actually is very close to 0, then we are getting that Green's function is very highly oscillatory in nature. Now, you see that in the next figure also I can see that this is the value for del g del z. So, when that mu is close to 0, you can see that how divergence it is. Now, it is actually that is the typical problem of this time domain panel method. The solution sometimes become the divergence, the solution does not come correctly, numerical instability is occurring because of this these things. Now, you see here otherwise if you just mu is somewhere away from 0, okay, so then you can see very nice convergent solution. So, now you have to remember, so this sometimes leads to some kind of instability. Okay. Otherwise, the results normally is pretty good. Now, I just have some kind of vessel. So, these are the 3 different type of ship, and then you can see the results are normally this is very stable, and then it is matches nicely with the other experimental results or other thing. Okay. So, we can see the results are pretty good. However, if I take some kind of vessel which is having is a flare. So, that means if I look at the profile view, some ship sometimes have some flare here, transom. So, once you have this sort of thing, now you can see over here, and also you can see here also you can see some kind of the flare is there. Now, what is happening mostly in the fishing vessel will get this, we can see the results are actually instable. Now, what would be the reason for this instability, and this is the classical problem of forward speed time domain. Okay. Then it means that some geometry it will work nicely, but some geometry when they have some kind of flare at top like so it will not work. It is actually that is what is happening. Now, how to handle this in numerical instability? You can see here this value reached to 10 to the power 6, which is actually not reasonable. I mean, it is absurd, I would say. So, now actually we have to take care 3 things. So, let us see. Now, the first thing is that when normally most of the time we ignore this cross coupling C35 and C53 term. So, sometime we ignore this C35 and C53 term. So, this is one wrong thing we do, we should not do that. So, this is the first thing you should be very careful when you write the code. So, do not drop these two terms. So, keep this is the first thing. The second thing is that in the equation of motion, whenever you are normally what you are using is the Euler scheme or predictor scheme. So, what we are using that when do the velocity, we are using the present time step and we are approximating the future time step. But in case of a displacement, we are using the V t plus delta t, that means the implicit scheme for the displacement. Here actually what it is I mean I would say that there is a, I do not see the solution, but it works most of the time. So, what actually we are using that now first we are trying to get del phi del t with the forward marching scheme, and then we are getting the force and the moment, and then we are using the predicted velocity using the any kind of Euler scheme or whatever the scheme, and then we approximate the acceleration f using v t plus delta t, what we actually obtaining over here, minus v t divided by delta t. Now, I know that the dynamic force balance equation tells you m into f t plus delta t is equal to the force at t plus delta t. So, what we are going to do this we are using this technique to approximate the force in the next time step. It is an approximate force. Now, we are using this approximate force here to get the corrected velocity. So, actually earlier we did not use this technique to approximate the force in the next time step, but now we are using it. Okay. So, we are getting the force in the next time step, and similarly from here we can get the displacement in the next time step. So, you can modify your numerical scheme in this way. You are getting the velocity, then using again forward difference scheme to get the acceleration, then mass into acceleration you predict that is the total force in the next time step, and with that actually you try to figure out what is your the predicted velocity or corrected velocity. So, this is one scheme that we use and it works nicely. But the most important part we are here the behavior of the Green's function near free surface. As I told you, it goes to infinity in this way. So, we try to avoid the situation when mu equal to 0. Now, when the mu equal to 0 is possible. Now, if you go back to our previous idea, so we can call this is your theta. So, this sin theta should be 0. It means that this means that it is that z of t and z of tau if both are lying in the same horizontal plane, and which is happening in case of a flared ship. Now, you see in case of a flared ship what is happening, I will show you. In case of a flared ship, now if you have this panel, and if you have this panel, both are in same horizontal plane. Now, since both are in same horizontal plane, then this angle theta is tending to 0. So, that is what happening. Now, if you have a vertical panel, now this vertical panel cannot be 0, it is impossible. It only happen for the horizontal panel. If the panel is horizontal, this panel also horizontal, that time only this sin theta can be or mu can go to 0. So, we understand this. So, this is the problem with the flared ship. So, what actually here we do as a solution, it's very interesting solution. What we do is we actually use some kind of artificial paneling. You see here I have this layer shape and here I can use the artificial paneling to make some small vertical panel. It does not increase much the hydrostatic thing or other thing, very tiny, very small a vertical strip actually I attach to the original shape. Once we do that, you can see we can get a remarkable result. Earlier it was, earlier the force is going to 10 to the power 6 and now you can see we can get very regular, very nicely the results which is very sinusoidal, right. Now, see this is the thing that we would like to tell you about this the panel method thing. This is the strategy you have to use, okay. And now we are now okay with this linear formulation of this time domain panel method, and from the next class we are going to study or discuss about the time domain non-linear panel method. Thank you.